well introduced earlier today, I've been thinking about heterogeneous teaming for a very long time. And so I'll tell you a little bit about some of the work we've been doing lately in this area. So for really my whole research career, I've been thinking about how can we get heterogeneous teams to work together with certain kinds of characteristics. Obviously, we want them to be able to share resources that they have available with each other. We want them to be robust. We want them to be adaptive and to learn. And we want them to be able to communicate implicitly in particular, and also to work with human teammates. So the very earliest work that I did in this area was really suggesting that you ought to have heterogeneous robots work together without directly having conversations with each other about who should do what. So it's very much this idea of implicit communication. How can they figure out on their own what to do? But 20-something years ago, the ability to have robots to be able to observe implicitly what other robots were doing and then be able to make decisions, it was a little premature for that. And so, of course, more recently as well, I think the ultimate in heterogeneous teams are teams of people and robots, and different kinds of robots. And so more recently, we've been thinking about how can we get teams of robots that include people to work implicitly. And so a lot of what I'll focus on today is really how do we get the teams that include people to work with these heterogeneous robots. And we call a lot of this work peer-to-peer teaming, where peer means the human and the robot are working together as teammates without one telling the other what to do. So really getting around the command and control challenges of a human telling a robot what to do. We want the robot to be able to figure out how to collaborate with the robot effectively on its own. And obviously there are lots of application domains that drive this, such as search and rescue or elder care, education, security, and so forth. And in all of these, we have some of the same kind of objectives, which is that you would like the robot to be like a person, in that it just understands what the team is doing and figures out for itself how to be a collaborative partner. So in peer-to-peer teaming, of course, there are lots of meanings of this. I don't want to go into a lot of detail on these definitions. There are lots of different kinds of characteristics. Let me just tell you what it is that we think about when we think of peer-to-peer teams. So these are humans and robots that are working together in the same physical space. They're working on an activity that they have, they're cooperative, so they've had some sort of shared knowledge about what the goal is of the team. They want to work together, so these are not adversarial people or robots. They're trying to work together towards some shared goal. They want to be as helpful as possible, but they also may have some individual pieces of the goals that they need to contribute to themselves. And it, of course, assumes that they have enough common ground that they can actually accomplish this in some meaningful way. There may be some learning that takes place in order to get to that point. But this is kind of generally what we mean when we talk about how the humans and robots work together. What we're working on now is actually teams of humans working together with teams of robots that are heterogeneous. I'm going to talk about today, though, just how do you get one human and one robot to work together, but again, with this idea of how it's can scale up. And again, I mentioned some of the goals here. If you think of search and rescue teams, these are people that have trained together over and over and over, and they know how to work together. They know who is better at what, and they just do it through training. They're just able to interact without a lot of direct discussions about what goes on. A fire team of soldiers that are clearing the building do this quite well. They've trained together over and over, but when they go through the building, they know who's best at what, and they can read each other's body language. And so this is really what we want to get to with robots, is to have these combinations. And it's really the key challenge, in my opinion, though, is this implicit communication, this implicit understanding of what the other teammates are doing. Now, you can study this just with robots, and there's some early work that has studied this just in the context of robots, trying to understand what the state is of other robots. A lot of times this has to do purely with their position in the environment. So it's certainly much more challenging to do this with humans as teammates. But I think as you get to more and more robots with more capabilities and heterogeneity, perhaps there are other indicators as well. So, what are the challenges? You have to understand the goals and intent and the actions of the teammates. You have to know how to represent those. These are heterogeneous teammates, so it may not be exactly what the robot that's learning or interacting knows, or how it can perform tasks. It may be different. So how do you represent that when it's heterogeneous across multiple kinds of teammates? How do you decide what to do? This is the canonical action selection challenge. And of course, how do you adapt and ensure that it's robust and reliable? So our approach to looking at this in the human-robot interaction domain has a heavy reliance on the perception and understanding what the people are doing, with then the use of what's being perceived for the purpose of the robots being able to decide what to do on their own. And so this is some work that we've, sort of the pipeline that we've put together that we're working on now. So you have the ability, of course, to understand what the people are doing, how you represent what the people are doing, and then understanding how to select the appropriate way to contribute to the actions or the tasks that the people are working on, so that you're contributing to the same goal. Now, we're doing this in the context of this robot we call Rosie, is our sort of humanoid robot that we interact with for some of these human-scale interaction tasks. This robot, of course, has lots of sensors on it, has the ability to, she says very freedom arms and hands and so forth, so it can do human-scale tasks a little more easily than some of the robots we've traditionally used that run around loaded around. As an aside, we've used this robot. This is my student Chris Reardon, who's now at Army Research Lab of all places. But he used this robot to train students with disabilities to teach them life skills. And so the idea is that the robot would observe the student as the student is trying to do a task like make change, for instance, or do some sort of assembly project. And the robot would observe the student as the student is attempting this task, and then would provide prompts. And so we studied different kinds of prompting mechanisms so that the robot would provide the proper prompts for the student to learn the task. You don't want to provide too many prompts, but you don't want to provide too few either. So he looked at strategies like systems of least prompts, systems of most prompts, and so forth, so that you can then interact with the student. So as the student learns, the robot can understand the state of the human, their level of understanding of the task. And so that's another kind of implicit interaction, and that, again, the human is watching the student as they perform a task for the purpose of prompting them appropriately when they seem to get stuck in some part of the task. So I'm not going to talk about that, but that's another direction that we've taken this in the area of robots serving as teachers for students that are learning physical skills. And so in the area of really understanding what the human teammate is doing so that the robot then can contribute in some meaningful way, we've looked at a lot of different aspects of this problem. One of the things that we did early on was to come up with some features that help the robot to more quickly and reliably detect the human activities. And of course, these are in context where the human and the robot are physically moving around in a space, working on a task. You're not just watching a video of the human, but you're physically working with the human. and you may have different vantage points and so forth. And so we developed a couple of features that were relevant for this domain, a depth of interest feature and a simplex-based orientation descriptor that we show provide particular high-quality feedback for the purpose of real-time activity understanding when the robot is working together with human teammates. Typically, because you have teams of robots and teams of humans, you need to be able to do this again in real time with multiple people and multiple robots. So we have also made some contributions in the multi-human perception domain, again, where the robot is physically in the same space with the human running around amongst the humans. And then at the same time, multiple humans doing multiple kinds of tasks. So the activity recognition problem with multiple robots going together with multiple humans. And then the question of how does the robot know what to do for the purpose of contributing to the task at hand. So this is what we call risk-aware action selection, which is knowing that there's some potential error in the understanding of what the human is doing. The robot may have some risk at making the wrong decision as to what the human is doing. And so the robot has to select an action knowing that it may be wrong based on what is perceived. So that's kind of the risk-aware action selection piece. So let me just kind of quickly tell you about some of these pieces. When we started this work a few years ago, this is when the Connect had just come out, and so we developed this depth of interest feature that is very easy to calculate, it's very quick, and it's very useful for this domain. And so we make use of that to develop what we call a 4D local spatial temporal feature that, again, works very quickly in the domain of humans working with robots, so that the robots then can classify the actions that the human is working on and then contribute to the task. The main characteristic of this particular feature that we developed is that it's a local feature, and so rather than looking at things like skeletal models or 3D trajectories and so forth, this brings together lots of local features and makes it very robust. In the theme of robustness, it works quite nicely. There's some related work in this area. And so with this 4D local spatial temporal feature extraction approach, we apply this feature detector across the entire image. You're looking for local features that are relevant to the task at hand. You can combine both the spatial aspects to it and the temporal aspects to it in the same feature, so that you don't have to use a temporal model for learning. You can use even models that don't explicitly measure or model for time, and it actually still works quite well. And so by applying both this Gaussian filter along the spatial dimension and the temporal dimension, you can very quickly get a combination of space and time information that works very well in real time. And so this is applied across the entire image. We combine in weighted sum the intensity with the depth information that you get from the Connect. And then we use a code book in order to come up with the various types of features that we expect for the different activities that the human and the robot are working on together. We use an LDA approach in order to model the different activities and features that you would expect for the different activities that the humans are working on together with the human with the robot. And so the different combinations of these code books of features can very reliably be used to detect different kinds of activities. And then the neat thing that we take advantage of out of this is the fact that we now get a distribution of activities of what it is that we think the human is doing together with the robots. And this distribution of activities gives us a lot of information that we can take advantage of for the purpose of doing the risk-aware action selection later on. And so by knowing that the human is most likely doing task A, but it might, with a fairly reasonable probability, be doing task B or C, we can incorporate that entire distribution into the risk-aware action selection. And so we implemented this in a domain that was sort of like just a variety of different actions that the robot might be performing. We also compared this to a lot of the existing data sets that are out there for the purposes of comparison. And again, you can, in real time, be able to detect the features of the human, what the human is working on, and understand what it is that the human is doing for the purpose then of the robot chipping in. Now, these particular activities are those that are found in traditional data sets for the purposes of comparison. Since we didn't have data sets that allowed us to do sort of store activities, which is what in this work we had a robot working with a human and sort of store kinds of activities, but there were no existing data sets that allowed us to compare our approach with the standard literature. So these particular activities are the ones that are in the standard data sets that you see. So there are papers here that talk about the evaluation on these systems, and I won't dwell on all of this. The point here is that this approach has been shown to be effective for the purpose of having the robot understand what it is that the human is doing. Now, the real question then is what does the robot do in response? I have some more information here. Again, all of this is in papers that we can talk about. Some other kinds of features for multiple human detection and tracking. I don't want to go into all of the details here. Again, another descriptor for activity recognition with robots that has been shown to give a much higher solution quality. Again, there are papers that can go into these in more detail. And then there's a question when you're working with humans, with a robot working with a human, the human is going from one action to another action to another action. It's not like just a video sequence that's labeled and it says now you're doing X. Then you go to another labeled sequence that's doing Y, and another one that's doing Z. You don't have these nice clean divisions. So the robot now has to know when the human is transitioning from one activity to the next to the next. And so this is really the challenge of understanding continuous human activities while the robot is working with a human. And so we've also done some work in being able to have the robot be able to use these distributions that give you the probabilities of the different activities being achieved by the people in the environment, and then being able to recognize when there's a transition taking place from one kind of activity to the next, and then taking advantage of that as the robot decides what it should do for itself to help. So again, we have some work in this domain that this is, you can look at more of the details in the papers, but the colored lines here at the bottom show that the approach for detecting when you're transitioning from one kind of activity to the next is very consistent with what people think are happening as well. So it's kind of small. The one in the middle is the human estimation. And our approach is the color line on the top. Each color represents a different kind of activity. And so it matches pretty closely with what people think is actually happening in the environment as well. And so let me just then mention, again, the overall scenario here, as you can see. And what we're working on right now is this risk-aware action selection. We had a paper on this at this past ICRA. But again, this is getting how can the robot know what to do, given that it's figured out what the humans are doing in the environment. And taking into account that these robots may be wrong, it's implicitly trying to observe what the humans are doing. And so therefore you want to be able to mitigate possible errors of making the wrong selections. And so it takes into account the risk of the consequences And so that, then, I'm getting the time signal, so just acknowledging some of the students that worked on this. Okay, so that's a quick view. Any questions?
Well, thank you